thank you for the nice introduction. I'm really happy to be back here at this stage to explain our progress in the quantum computing at Fujitsu. I switch to Japanese from now. Okay. どうもありがとうございます。
Thank you. Sato from Fujitsu. Q2B last year was held for the first time in Japan, and I had the opportunity to speak at that time. Q2B Silicon Valley, I also had the opportunity to speak there. So it's been a little over 6 months. So I'd like to talk about the recent progress since then. This is the outline. Explain the background, then talk about our quantum computing. Not just real quantum computing, but the quantum-inspired technology as well. Digital annealer is what we're working on. So I'll give you some recent updates and some use cases. Showed this last year as well. We're a computer company at Fujitsu, so over many years we have done R&D for computing technologies from the mainframe days. Still working on the HPC and FX10. We developed together with Riken. This is the uses the same chip as the K supercomputer, and the FX1000 use the same chip as Fugaku. It's the HPC, and so we're continuing our HPC research, but in terms of computing performance enhancement, well, it's been slowing down gradually. So architecture focus on application. People are developing that. AI chip is one example. In that context, we have digital annealer that is focused on combination optimization. And then for the future, we're working on the quantum computer as well. Last year, computing as a service vision was announced. It's a platform that we created and we started offering to our customers. So we take our computing technologies, we want to offer that widely to customers through this platform. In the future, customers, they don't have to think about which computing technology to use, and they can solve the problem. We want to make it that kind of a platform. So currently, HPC, digital annealer, comprise this platform, but we want to add quantum computing there as well. Next 10, 20 years, quantum computing will probably not solve all the problems, and so various computing technologies should be combined to solve customers' problems. That's our approach. So let's talk about the gate quantum computing first. This page shows our strategy. Basically, as shown, from device level to software and application, in all layers, we have collaboration, working together on joint research with other institutes. For hardware, the final solution is not clear, so we are working in several technologies in parallel. So superconducting qubit, we're working with Riken and with TU Delft. We have the diamond spin technology. And we have Professor Ishihara from TU Delft explaining at the booth. And also software, not dependent on hardware, is where we're focusing on. So error suppression, error correction, we're working together with Osaka University. And also application, how to use quantum computing in the future. We think that's important. And a quantum simulator we have developed using Fugaku technology, and since last year, with Tokyo Electron and other customers, we've been working on developing applications. So hot topic, this past March, Riken has announced the first quantum computer. We are part of that effort, and in autumn, Riken RQC Fujitsu Collaboration Center, which we established 2 years ago. So from there, another 64-bit machine will be made available. And Riken is doing various things for the academia, but in our case, we want to develop application for the industry to be used together with the simulator. So chip, it's being displayed at our booth. So this shows the chip structure. So no interconnect, but Dr. Nakano designed this, the basic design. It's basically 3D interconnect, 3D contact. So interconnect is on the back side of the chip. What's good about that is that when you scale up, you don't have to change the design. If the wiring comes from the side, you have to change the design. Certain companies, the chip design has to change every time you scale up. But with this, we can go to at least 1,000 qubits. Well, with wider area, there will be uniformity and other issues. But at the wafer level, how to make a uniform qubit, that's a technology that we're working on. Simulator, I mentioned a bit. So we use Fugaku technology. So it says fiscal 21. So that was March last year. 36-bit quantum computer simulator was released. At that time, that was the fastest in the world. And then we continue to scale up. And now in July this year, this month, 40 qubit simulator will be released. Compared with 36 qubits, that's 16 times the scale. And it's being released soon. And so using this kind of simulator, we work to develop applications with our users, like Fujifilm, Tokyo Electron, Mizuho, Daiichi Life Financial Technology. These are the partners we're working together with. In parallel to that, we're working on the Quantum Simulator Challenge. And so we provide a simulator for free to various customers to do application competition and give a prize money to the top 3. So the simulator that we provide is a state vector. But for their customers who want to use larger qubits, and so with the Barcelona Supercomputing Center, we're working on the tensor network simulator. Also with University of Tokyo, we're developing on simulator using the decision diagram method. So we will have the actual machine, but with a common platform with a simulator. It's a hybrid platform, so that the customer can use both. And so they can develop applications on it. And on the platform, we work with Kinesis organizer. So their software, Kinesis software, will be usable from the platform. And using AI, optimal computing resource selection, that kind of software technology we have. So we would like to gradually put that on this platform as well. The other technology we have, diamond spin technology. And in our booth, we're displaying the chip that's being developed. Sorry, it's a busy slide. So one module is like a center and has this electronic spin and a communication qubit, nuclear spin. It's one module. So it's a modular diamond spin technology. We're working with TU Delft. It uses a photonic link, so it's relatively easy to scale up, we think. And operation temperature is relatively high, so cooling load will be lessened. We're still at the basic research level, but for the future, we are working on this kind of technology as well. So this is the chip that we're displaying today, a diamond chip on a silicon nitride waveguide. So many modules will be integrated on the chip. This is technology that we have. We're also focusing on software. I've used up too much time already. Error correction technology we're working on, and together with Osaka University. And in terms of error tolerance, 1 million qubits you need for tolerance. But currently, it's several hundred bits with NISQ. several hundred bits and million bits. There's a big gap. 10,000 qubits, not much use for NISQ. With a larger number of qubits, the error requirement becomes more demanding, and so you can't use it unless the error goes down. At 10,000 qubits, is there any architecture where that can be useful? We've been looking for that, and this past March, together with Osaka University, we put out this press release, and I'll explain that a bit more. So this is FTQC using SAS code, and basically we're thinking about using lattice surgery. So there's a basic gate set and logical C0 and logical S and logical H gates, and H and D. By repeatedly using that, you can have a rotating angle. The T gate is very costly, upstream process and all, and you can't take it to the desired angle unless you do it 50 times, and so it's very costly in terms of qubit. And so logical T gate, we want to replace it with a phase rotation gate, partially physical. That gate not perfectly error protected, but by using this, physical qubit number can be increased 1/10, and gate operation can be reduced 1/20. And I don't have time, so well, you can read the details in the paper. It's like a phase rotation. It's like 4112 code. It's like a small surface code embedded, and it's like a distance 2 code. So if there's an error, it can be detected. So going through that process, error rate can be reduced to 2/15, and then that can be applied to larger qubits, and then you can teleport to the gate that you want to rotate to, and then you can realize any rotation angle you want. That's what we're proposing. And this process, we know that on average it's successful in 2 trials, and so you can realize rotation quite easily. And error rate very low, and the rotation gate error rate impacts operation number directly. So relatively, if you assume relatively low error rate, what can we do with 10,000 qubits? And so there was a T-gate structure I talked about. With 10,000 qubits, not much can be done. Vertical axis is speed, horizontal is the number of logical qubits. With 10,000, with the ordinary architecture, can't do good calculation. But if the physical error rate is 10 to the minus 4, with 10,000, then you can realize 64 logical qubits. And then in the relatively near future, we can have a realistic quantum computing. So this is a theoretic paper, but we can implement in software. What is needed to implement in software is the research that we're conducting. I've used so much time, and so we're focusing really much in software. This is proof. Past 2 years, all the papers we've published for software algorithm, error correction, decoder, error mitigation, etc. All these papers, Eigensolver as well. So please take a read if you have time. And have to talk about the future, the roadmap. So 40 quit qubit quantum simulator this year, and 256 qubits in 25, then 1,000 qubits fiscal 26 onwards. That's the plan. I'm running out of time, so I'd like to talk about the digital annealer. Sorry for the busy slide. To make a realistic quantum computer, it takes time. So quantum-inspired technology, digital annealer, is what we've been working on for about 5 years. Well, actually, we launched about 5 years ago into the market. And basically, all the bits have a full connection. That's the uniqueness of this. Details here. Past 5-6 years, developed various technologies. We're number one in the industry in terms of our capability to solve problems. There are various constraints in actual problems, and you have to consider that in solving them. So we have technology to handle those constraints. And as a result, this digital annealer is being used by more than 100 customers. This is a roadmap. 2016, we started research. 2018, the first generation was launched. That was about 1,000 bits. Then second generation reached 8,000 bits. Third generation, software and hardware combined in this architecture using 8,000 chips to solve 100,000 bit problem. Next year, last year, fourth generation using GPU, large core. So 100,000 bit problem can be solved without partitioning. And we're making the fifth generation now. And then, so you're solving 2D problem, but with fifth generation, we'll have an architecture where you can have higher order terms. And this is the fourth generation explanation. So with the third generation, small hardware is handled with software to solve 100,000. But the fourth generation, 100,000 bit problem can be solved without partitioning. And then similar size problem can be solved 10 times faster. That was the fourth generation. And we have the interface to enter the constraint terms easily. And some technologies we're working on recently. One is IntelliTune. In order to solve problems with DA, there are various hyperparameters, and in order to adjust, you need skilled engineers. And in spreading digital annealing technology, that was a big problem. So hyperparameter, we automatically tune using AI, and this technology is being improved. And so even if you don't have skilled engineer, you can solve problems now. Right-hand side, this is a higher order terms solution. So in the past, you had to convert to quadratic, but now you can directly solve the higher order terms. So that kind of architecture we're developing. Several use cases I want to explain. One is NYK, Nippon Yusen. So you load cars into a ship, and it's a big calculation, 7,000 vehicles in 12 floors. As you can see, there's a huge amount of patterns, 10 to the power of 2,000. So experienced people, based on their experience, were solving this, but with digital annealer. We can reduce 4,000 hours of work. Next is manufacturing. With Toyota Systems. So car manufacturing line, you have multiple models and colors in a line, single line. So in what order to make is most efficient, that's very important to reduce cost. And digital annealer is being used to solve such a problem. And that was done experientially, but now that's been made automatic. And it's actually been introduced into the Tsumi plant of Toyota. And so now this will spread to other plants in Japan and abroad at Toyota. The last one, I talked about this previously, drug discovery. And so with, you have the substance, you want to see if they connect or they bind to the protein. And if you do this with HPC, it took a long time. So with DA, we did this together with Pepti Dream, using DA, make some model. By using DA, HPC usage time was greatly reduced. And what used to take 2 weeks can be done in half a day. So it's very efficient. In a short period of time, you can narrow down on the candidates. So with the DA, you do rough screening, and then with the HPC, you can do more rigorous screening. And then with that, you can reduce the calculation time quite substantially. So that's another use case. I think they'll tell me to stop. Concluding remarks. So quantum computing, we're seriously working on this fiscal year. Finally, 64-qubit superconducting computing system will be released from RICAN. And for a true quantum computer to be realized, it will take some more time. But together with our joint research institutions, over the long term, we're going to work on this. And HPC and DA technology we already have. And to solve customers' problems, we want to capitalize on these computing technologies to solve various societal issues. Sorry for going over time. That's all from myself. Thank you for your attention.